Give me 1 second. And the computer is a bit slow, so give me some time. Let me check. Okay. I'll give you all the details on how to access the lectures for offline viewing later on. Okay, so this is for me a new experience. It's the first time that I teach a soft skill teach a course focusing on climate change. I already taught courses focusing on climate change within the School of Engineering. And climate change, Francesco, I think I am back. Okay. It crashed actually, so if it happens again, I'll, I know what to do. I can't hear you for some reason, so I'm not sure if you're muted or not. Okay? Okay, perfect. So, as I said, this is the first time that I am specifically, just 1 second. Okay, now we are okay. Should work. Yeah. Okay. So, as I said, this is the first time that I am teaching a full course focusing on climate change. I will not be teaching alone, as I will tell you later. So this is, for me, a double experiment. It's an experiment because it's a soft skills course, and it's an experiment because it's my first time focusing on this topic, precisely on this topic. And, I think the fact that I am expecting a lot of students of which only a small part is from the School of Engineering, it makes a big difference for me because I am committed to teach in a way that is useful and at the same time comprehensible to everybody. So I will take care of this. And if you have any critical comment to give to me during these lectures, like you think that your background doesn't allow you to follow me, or my teaching is too technical or too trivial, I would appreciate very much if you helped me in making this experiment successful. So what I really would like to do is to have interaction with you all. An interaction where I am expecting all of you to learn something. And actually, this is a topic, climate change, is a topic where interaction and exchange of views and opinions is an essential ingredient of a successful recipe. And our target is to learn more about it, to learn about the science behind it, but also to learn what is the communicate about climate change, what is the best way of speaking with an effective voice. Because as you know, one big problem with climate change is communication, is the fact that it's difficult to convey to people, to the person in the street, the essential behaviors of this problem. So I think that this interaction that we could establish each other, which is of course interdisciplinary, it may be very useful also to contribute to solving the problem. What we aim to do by studying together, by discussing together, is to effectively give a contribution. So it's not only education. Education is, of course, our primary target, but our target is also to make an effective, to give an effective contribution. Okay, so I think the best way of introducing this. Okay, we should be here again. No. Yes, yes, you are online. Now you should give to me the right to share the screen. Okay. I think also, let me see. The registration of the lecture, I'm not sure if it's active again. Okay, that's perfect. Thank you. Now let me share the screen again and let's see if it works. Okay, this is my website. It's divided into columns. So you find teaching on the left and research on the right. Let's go to the link of our tutorials. You see here, tutorials of science of climate change and climate actions. If you click here, there is the full description of how the course is delivered. And I will go through this page together with you in order, give me the first half an hour in order to clarify how the lectures will be delivered, how the exam is done, etc. And I refer to a modified version. I'm sorry, let me just, okay, let's stay here. Now, the study plan is summarized here. And these are the topics I would like to discuss with you, together with the other professor, whom I will introduce in a moment. And here there is a bullet point, which I'm not sure we will be able to deal with, which is environmental economics, because we managed to place all the lectures into their time slot, and it seems that we have to cut something, and probably it will be environmental economics. But this is something that I will confirm to you later. Now, this is the calendar, and the calendar gives to you also the name of the professors that will teach together with me. The first two lectures will be given by me, and also the last one. The other lectures will be delivered by the professors that you see named there. Actually, I think there is connected Professor Alberto Bellini. And Alberto, if you would like to say something to students, just to introduce yourself, your background, you are very much welcome.
Can you hear me?
Yes, perfect.
Okay, good afternoon to everybody. Thanks, Alberto. It's a pleasure to meet you. I'm a professor of electronics and electrical engineering, and I will give you some short information about the energy conversion with special reference to electrical energy conversion and environmental impact and process of the energy conversion, distribution, and use in our communities. So thanks, Alberto, and I give the floor again to you.
Thanks, Alberto Bellini. And the other professors could not connect today. You see the names there. When they will deliver the lecture, I will be attending the lecture anyway. So I will be present at all the lectures. You can understand the pros and cons of involving several professors into a course. The pros is the advantage is, of course, that you will listen to the best experts from their field. And these professors are, I think, able to give you an up-to-date view of the science of climate change. The disadvantage is potentially that you will not listen from only one voice, but from several voices. We made our best to coordinate, and I will also attend all the lectures to make sure that everything is coordinated. I think this is an interesting solution, especially for this topic, because climate change is a multidisciplinary and interdisciplinary problem. So I think this is the best solution, but we are also looking forward to getting your opinion on this. It will be, for us, very important to shape the course for the next years. And I just would like to say what is the reason why we named this subject in this way. It's named Science of Climate Change because we are interested in the science behind it. Science may also involve communication, may involve all the disciplines, all the relevant disciplines, but we are really interested in the science. And we are also interested in climate actions. Climate actions are the actions that we need to take to mitigate climate change and adapt to it, because we will discuss about two categories of actions: mitigation and adaptation. Mitigation means that we do something in order to reduce climate change. Adaptation is instead are actions that aim to limit the impact, the negative impact of climate change. These two categories of actions are to be studied together, according to our opinion. And action is essentially, it requires a strong interaction with engineering, because many of these actions require also technical design. Of course, we are not focusing on the details of the technical design, but we want to understand what is the best way of shaping these solutions. Now, tutorial documents, they are accessible from Virtuale and from here. Here you see the link of the first lecture that is given by me, and it is given in the form of a web page, because I decided already some years ago to write all of my tutorials for students in the form of web pages, because this allowed me to include links to relevant information on the web. Keep in mind that when we talk about the science of climate change, we cannot use a book. We need to make reference to the up-to-date, to the latest scientific contributions. And therefore, the access to the web, to study on the web, to get the information from the web is necessary. And this is why I decided to use web pages for providing my tutorials. The other professors will provide their tutorials in a different format. It may be a PowerPoint presentation, it may be a PDF. Everything will be linked here and in Virtuale. And you see that the list is now including only the first lecture, which I hope to start delivering today. Not I hope, for sure I will start delivering today. And the reason is that we are, given that this is the first time, we are preparing the material. The material will be made available before the lectures, but it's not ready yet to be made available today. So this is why you see only the first link. But for the next week, I will put during this week the second link and so on. Now, as you know, the lectures are delivered both in physical presence and in streaming. Please be aware that if you want to attend in physical presence, you have to book your attendance on presente.unibo.it. If something happens that we cannot continue in physical presence, it's no problem at all. We turn to full online teaching. You are used to it, we are used already, so this is not a problem. The lectures are recorded, as I said, and the videos will be made available on my YouTube channel, which is accessible here. You see, follow me on YouTube. Here on my YouTube channel, you can find all of my lectures, and you will be able to find here, if you look on playlists, you will be able to find here the playlist of this course. It's not yet there because it's, just one second, because it's still empty. It is already created, but it's empty, so it's not visible. But from tomorrow, as soon as I'm able to upload the video, you will be able to find here the video, the playlist of this subject, and the video of today's lecture. So again, they are available on YouTube, is open to the world. Okay, and what can I say again? Just 1 second. Exam. Now, you are many students. As you know, this course had 200 seats available. They were fully booked. So you are many students. So the exam will be organized in the form of an online exam through a quiz. And you know that the mark is to be given in the scale 1-30. Let's hope that we don't start from 1, of course, and joking. And I'll organize the quiz in a way that will allow you to carry out the exam in a reasonable time, I would say half an hour. And I will give you detailed instructions later on. I will also give you the opportunity to test the quiz before the exam. The exam can be taken only when the lecture period is closed. It means after June, I think, from June 7, I think. Let me see if I can uncover here. June 7. So after June 7, we will schedule immediately an exam, and other exams will be scheduled later. In June, I plan to schedule 2 of them and 2 of them in July. So you will have plenty of opportunities to take this exam. And if you have any question regarding the exam, regarding the tutorial documents, please feel free to step in and during the lectures or in the chat, or you can write an email. Okay, just please keep in mind that you should preferably, if you have questions, please preferably ask the questions during the lectures. The reason is that in this way everybody can listen to the question, and the question and the answer may be useful to everybody. And also, given that you are a lot of students, if you start writing many emails, I may have some problems in replying to everybody. So I prefer to get the questions directly during the lectures. And of course, you can use the email in case you have a urgent issue to ask me or to resolve. No problem at all. I just wanted to make you aware of my preference. And again, the type of questions that I may ask in the quiz, I will give you clarification later. I will give you examples, okay? In order that you can prepare in advance, you can get in advance an idea of how the exam will be structured. Okay, I think that's it for the logistic. I wonder whether you have any question before I continue. Okay, and I just would like to give a couple of words to introduce myself. Ideally, with my students, usually we make a round of introduction. With you, it's impossible because you are too many. And but I think it's useful for you to know something about myself. As I mentioned to you already, I am professor at the School of Engineering, and I am a civil engineer. My field of research is the water cycle. It's the science of hydrology. Hydrology is the science that studies the water cycle. And I am therefore an hydrologist, and in my research activity, I in particular focused in the past on water scarcity and floods, water resources management, and mitigation of natural hazards caused by water. And I became an assistant professor in 1998, so it's already 23 years that I am involved in the university. And during this period, I mainly focused on teaching and research and administration. I only did a little of professional activity. I make a lot of consultancy activities for the university to local administrations. And given my field of research, you can understand that from the beginning, I had to confront myself with climate change. And in a very applied manner, meaning that I am doing research in engineering, because hydrology is a discipline that has a strong interaction with engineering. And therefore, the problem is how should we design infrastructures, civil structures, by taking into account the new situation given by climate change, how to design a bridge, how to design the river training structures, how to design levees, how to avoid floods in the presence of climate change. And this was a very practical need that brought me to make a significant part of my research activity on climate change impact and climate change adaptation. Mitigation is not my field. And therefore, mitigation will be dealt with here in this course by another professor. It's not my field because mitigation requires a full knowledge of atmospheric dynamics, a full knowledge of climate science. I'm not a climate scientist. On the other hand, I had to establish strong interactions with climate scientists in order to be able to develop interdisciplinary research. Because for an engineer, it's not just enough to know what is the new condition. It's not just enough to know what we call design variables. It's not enough for me to know what is the rainfall that I may expect, an heavy rainfall, a storm that I may expect under climate change. I need another essential information, which is uncertainty. So I don't need just a number. I need a number plus a plus minus, plus a confidence interval, a range, because the engineer has the need to take uncertainty into account. And in doing this, I introduce a key challenge with climate change. The challenge is to quantify uncertainty. If we want to be effective, we have to know what we know for sure and what we know not for sure. And this requires a strong interaction with the climate scientists, because I need to know not just their prediction, but a band of what is possible. If I don't have the band, I end up underestimating the impact of climate change. So essentially, I'm a researcher. I'm not a big one. I'm not Mike Mann. I'm not Stephen Ramstorff. I'm not. I may make several other examples. On the other hand, I think I have a good knowledge of the literature on climate change. Literature, again, multidisciplinary. And keep into account that if you want to be effective, this is an essential requirement. You have to know the science behind it. And even if, no matter if you are an engineer, if you are a social scientist, if you are a communicator, you need to know the science behind it. And with climate change is a problem because the science is tremendously huge. It's massive. It's you know what happens if you type in Google climate change. And even if you type science of climate change, you know what happens, millions of entries. And it took to me really a lot of time for gaining, let me say, a minimal knowledge of what's going on in the scientific arena. Because it looks like a very simple question, like climate is changing, we need to do something. No, it's not simple. Absolutely. And my aim is to clarify with you what are the open questions, what are the models that we use, what are the observations that we use in order to try to resolve these questions. Because once again, we need to make sure that we have a full knowledge of climate change and its uncertainty. Okay, so this is my introduction, and I wonder whether, once again, you have any question. And keep in mind one thing, today I'm not insisting. Already next week, I will force you, when I ask for questions, to ask at least one or two, depending on how many you are, because we really need not to be shy, we need to interact, okay? So I'm not sure if you have clear what I mean with uncertainty. If it's not clear, you should step in and say, can you please explain better? You have to help me, because it's the first time. Okay, I also taught 1 year at the high school, but I was saying it's the first time that at the university I teach to not engineers, students not in engineering, which is for me kind of, let me say, I think I am lucky. It's a fortune.
Sorry, teacher, can you hear me?
Yes.
I would like to wanted to say that in the chat there is some questions, so if you can read them and answer.
Yeah, I have. Let me say if I can, because it is okay. I think the questions are related to translation.
Also, yes, but if you go up, there are questions about, for example, the exam and stuff like that.
Okay, yeah. Okay. Okay, there is no WhatsApp group managed by me. Of course, if the students want to set up a WhatsApp group, is fine. Please don't ask me to join, because it would be impossible for me. And a penalty for wrong answers, I would say no, it's not a penalty. I mean, my intention is, first of all, let me say that I am open to your suggestions, but my intention would be to put a lot of questions with the score 0 assigned to wrong answers and a certain score assigned to the right answers. And there will be a threshold above which the exam is fully successful, meaning 30. My intention is that you don't need to reply correctly to all the questions in order to get the max, because I don't think really it is for a soft skills course. I don't want to be strict. And so the answer is no, there is no penalty. So it will be possible also to skip some of the questions and anyway to get the full mark. The grade will be registered as idoneity or normal grade. It will be a normal grade, not an idoneity. Okay, I hope it's clear. And I think that's it. And I can try to keep the chat open, but it's not, I may miss some questions. So thank you for letting me know. Okay. So, sorry, let's go to the first lecture. The climate change problem. Now, one thing, these lectures, these tutorials in the form of web pages are, I mean, in order to follow the lectures, are not very helpful because there is too much writing. So my suggestion for you is, I think they are best conceived for studying afterwards, but my suggestion for you is just to pay attention to what I say. I keep the web page open because it allows me to remind what I have to say and to follow a logical train of thought, but it's the suggestion that I give to you is just to listen to me. And of course, if you miss something, the page is useful because it's basically, it repeats what I'm saying. Okay. So the purpose of this first lecture today is, first of all, sorry, there is one thing that I forgot to say. We have 3 hours of lectures each Monday. My suggestion is to make a break every hour. Sometimes the students don't like it and ask me to continue for at least 2 hours without break. What I would like to propose to you is to make 10 minutes break at the end of each block of 45 minutes, at least when I teach myself. Which means that now I started at 45, in 12 minutes I will make the first 10 minutes break. The reason why I want to do this also, it's on my behalf, because for me, speaking with the mask is very difficult, and it's hard for me to speak for 1 hour and a half. So if you agree, I would prefer to make the break every hour, okay? And if you have something against this, just let me know, I can change, it's no problem. Okay, now, the purpose of this first lecture is to clarify the problem. What does it mean, climate change? Why it is a problem? You may say that this is trivial, actually it is not. And if we don't understand the reason of the problem, we cannot understand the solutions. So let me dedicate some time to clarify what we mean by climate change and why climate change became a problem only in the past 30 years and was not a problem before. This is extremely important, and I think we have to start from the concept of sustainability and sustainable development, because climate change is to be seen in this context. Climate change, why it is a problem? Because it may make our societal organization not sustainable. So what is sustainability? I think that you know what I'm talking about. Everybody knows what we mean with sustainability and sustainable development. Sustainability means that we have to make sure that our societal development is sustainable to give for the future generations, to give to future generations the opportunity to benefit from this development and to further improve it. It means that while planning our development, we have to make sure that we are not overusing natural resources. We are not overpolluting the planet. We are not compromising the opportunities for future generations. This is what sustainable development means. Sustainable development is something the humanity has to deal with since the beginning. We can find many examples of unsustainable developments in the antiquity. For instance, in the ancient Athens in Greece, during the Greek civilization, they had the problem of the waste disposal, because they were not equipped for evacuating wastes from the cities. They were used to throw the garbage out of the window. And of course, when the city grew up, this became unsustainable. And the same thing for wastewater, sewer systems. In the antiquity, people didn't need sewer systems. But when the cities increased in size, of course, they had the problem of evacuating wastewater, bringing wastewater far from the city, and later on treating wastewater. Because at the beginning, people just aimed to bring the wastewater out of the city and release the wastewater in the rivers. And then 100 years ago, they realized that the rivers were polluted. And it is a clear case of a development that was unsustainable. And then they built wastewater treatment plants. So, I mean, it's not a new concept. Sustainable development is not a new concept. But there is to say that the Industrial Revolution marked a shift. And the shift was due to the development that was stimulated by the Industrial Revolution. It was a huge development that caused, the first impact was air pollution. And people realized that this was a problem, because it was a problem for the human health. And a big shift was globalization, because in the past, sustainable development was a local problem. So wastewater for a city or the wastes from Athens, they were local problems, easy to resolve. With the globalization and with the Industrial Revolution that basically supported the globalization, we realized that sustainable development became a global problem. And once a problem becomes global, it's much more difficult to resolve it. First of all, for its extension, but also because, it's very easy to reach an agreement among few people. When the number of people, the number of countries increases, it becomes a real problem, because the economy connected with resolving the problem becomes more complex, more difficult to manage. So basically, here you can see in the web page, I gave some examples of unsustainable impacts of societal development. Intensive agriculture. Intensive agriculture turned out to be unsustainable. On the one hand, there was the demand for more food, so people tried to stimulate intensive agriculture. On the other hand, when the demand increases and increases and increases, there is a limit in the agricultural development, and there is a limit also in the resources that you can use. There is a limit in the water usage, for instance. Keep in mind, water is one of the resources that are under threat in the presence of climate change. And most of the water is used by irrigation agriculture. And also the construction of dams and river barrages. Now we are realizing that probably this is a solution that it's not sustainable in the long term. Of course, we built dams, we built river barrages because we needed energy and we needed water for agriculture, water for civil use. But we realized that dams are a solution that has not a long duration. The lifetime of a dam typically is 50 years. There are examples of dams we can stretch. We can get to 200 years if the dam is, the behavior of the dam allow us to do so. But still, it is a solution that has, a very short duration. If you think about future generation, 200 years is nothing. It is something that looks very long to us, because we are used to measure time with a unit that is corresponding to our lifetime. So when we say 200 years, it looks like something that we will not see, and therefore we assume that it's a very long time, but it's nothing. It's really nothing. Our grandsons will probably reach this duration. And also the demand for energy, it's unsustainable, because energy, how it is produced energy today. The renewable sources are still a limited portion of the total energy demand and the total energy production. And finally, the concentration of carbon dioxide. Our development was based on a continuous increase of human emissions in terms of carbon dioxide, CO2. And you know that carbon dioxide causes the greenhouse effect, which in turn causes climate change. So this is a list of unintended consequences of our development. And climate change is one of these unintended consequences. So what is climate change? Climate change can be defined. Let me read here. And just 1 second, I try to make it readable, especially for me. Perfect. So, climate change can be defined in this way. It can be defined as a significant and long-term change in the statistics of weather patterns. I will define what weather means, okay, later on, just in a couple of minutes. So again, it's a significant and long-term change in the statistics of weather patterns. Let me clarify. What do we mean with long term? We mean a period ranging from several decades, 30, 40, 50 years, to millions of years, to forever, let me say. When we talk about millions of years, let me say forever, okay? Which means that the weather pattern is changing for a very long time, okay? It may be a reversible change. When we talk about climate change, we don't necessarily mean irreversible. But you understand that when something is going to last for 50 years, 100 years, 1,000 years, it becomes close to irreversible. Why we are not necessarily implying irreversible? Basically because we hope to revert it. Okay, we are confident that if we take action, maybe that we can set back. Okay, so I think it is clear what long-term means. Just 1 second, I look at the chat. Okay. Now, given that we are focusing on the science, we have to make sure that we understood the definition. So I think it's better if we define also what is the weather. I think we all understand what is weather. We have the definition can also be given by intuition, but let's be very rigorous. Weather can be defined as the combination of meteorological behaviors at a given location and time. So example of meteorological behaviors are temperature, wind direction, and speed, amount and type of precipitation, rainfall, snowfall, sunshine hours. So again, these variables, when they are specified at a given time for a given location, they form the weather behavior for that location at that time. So I can say today in Bologna, the max temperature is 13 degrees. This is an element that is characterizing the weather in Bologna today. I can say that the relative humidity is 65% in Bologna today. It's another behavior of the weather in Bologna today. Okay, so keep in mind this connection, weather, meteorology. Okay, then what is climate? Climate can be defined as the long term. And again, we start from a mean of 30 years. A long-term distribution of statistics of weather condition for a specific region. It means that when we talk about climate, we expand the time scale. It's not given at a given day. We cannot say the climate in Bologna today is. No. Climate is a long-term window, refers to a long window in time, and typically also refers to a larger region of space. So we say the climate of northern Italy, Usually we don't say the climate in Bologna. It's not really rigorous. We have to compute this distribution of statistics of the weather. What are the statistics? For instance, a statistic that we all know is the average. And I think it is a useful example. The average, okay? Do you understand? Or mean value. It means that if I get the temperature in Bologna, for instance, in February, I shouldn't say Bologna, I should say the Emilia-Romagna region, but let me say Bologna. Every day in February, I observe the temperature in Bologna for 30 years. At the end, I have 28, sometimes 29 in February, observation times 30 years. From these observations, I can compute the average or the mean value. This is the climate in Bologna in February. So again, the average is a good example of a statistic, very simple. We all know what is the average, but there are more complicated statistics. And other statistics are the variability. And keep in mind, it is extremely important that you understand what is variability. It means that when you have numbers that go up and down, like the temperature in Bologna in February, it may go up and down. You can compute an average, but you can also quantify what is the variability around the average. It is extremely important when you talk about climate, because variability is what causes sometimes climate to explode. Variability of temperature is usually quite reduced. Variability of rainfall is much, much, much higher. And this is why sometimes you get a rainfall that is exceptional. An exceptional rainfall is produced by its variability. So it is extremely important that you fully understand, no matter what is your background, what is variability. There are other more complicated statistics. You may have heard of about skewness, about autocorrelation. We don't want to go into the details, but just beware that defining climate means defining a lot of statistics. Some of them are very easy to compute, like the average. Some of them are not so easy, variability. Some of them are very complicated, like skewness, which is, together with variability, what gives rise to very extreme outliers. We don't need to understand what skewness is. Just keep in mind that the possibility that some extreme value occurs is dictated by variability plus more complicated statistics. And the more a statistic is complicated to compute, the more data you need. So when you compute a statistic, there is uncertainty. So for instance, if you compute the average of two numbers, only two observations of temperature in Bologna, the average is not really meaningful. It's very uncertain. If you have 1 million numbers, the average is perfect. You are fairly confident that it's a good average, okay? For the variability, you need many more observations. For skewness, which again is extremely important in determining the extremes, you need many, many, many more. And this gives to you an important information, an important summary. I forgot to make the break, but I make it soon. An important summary. You need data to characterize climate. We will talk about this later. I think we can start for 10 minutes. Do you have any questions so far? Okay, so 10 minutes break.
Perfetto, grazie.
Prego. Okay, I think we can start. Francesco, I'm starting again. I got a couple of questions by your colleagues, which I think are of general interest. The first question is related to the possibility to, how to say in English, to not to accept a mark at the exam. I'm sorry, I'm now missing the word for rejecting or something like that. So if you get like 24, for instance, as proposed mark, you prefer to repeat the exam. I usually give this opportunity not only once, meaning that my answer is yes, you are free not to accept a proposed mark, how many times as you want. The only thing that I ask you is, in case you don't accept a mark, please wait for the next exam before trying again. Because there are some students sometimes that ask me to remake the exam one day later, which is of course not meaningful. It's nonsense. So the only thing that I ask you, given that I will fix an exam, let's say at June 10, and another exam at June 24, another exam at July 15, another exam at July 25, I'm just guessing, you need to wait for the next date before repeating the exam. And the other question that they asked me is related to the language of the exam. The language is English, but the exam is written. It's a quiz. And it's a quiz with multiple answers. I will give you the details later on, but it's not free text, what you will be required to write, because you are too many, and I need to rely on an automatic correction. And so the questions will be in English, but there will be no need for you to speak with me in English. Everything is clear? Okay. It may be in the multiple questions that there are more than one correct answer. This is possible, but again, the details I will give you later on. Okay, let's go back to our definition. So let me summarize, because we clarified what is a statistics, what is weather, what is climate. So within a scientific approach, to make a summary, when we say that climate change can be defined as a significant, I'm repeating the definition, a significant and long-term change in the statistics of weather patterns, we mean what? We mean that from a scientific point of view, usually we mean that we collected data on weather, like for instance, local temperature during an observation period. We collected this observation for a long period, okay? Like 30 years. We computed the statistics of this data. For example, the average. And then we say that these statistics changed a long time. And the change was a long-term change. So again, I collect data, I compute the statistics, and by looking at a long period, I see that the average, for instance, changed. So I am allowed to say this is climate change. It doesn't make any sense if you say weather change, because weather, of course, is changing. Today may be sunny, tomorrow is rainy. Weather, of course, is changing. When we refer to the long term, we expect that the behaviors of climate are more or less constant. If we see that there is a change in these behaviors, in these statistics, it's climate change, okay? Perfect. Climate change may be local or global. And keep in mind that local climate change can be even more dangerous than global. Think, for instance, at the situation in cities. Cities are the environments where temperature increased more, because there is the sum of climate change plus the urban heat island effect, which you can clearly perceive if you are a motorbiker. You don't perceive it during the day, but if you drive your motorbike in the night, you clearly perceive the change of temperature when you get into a big city. And the heat island effect may assume a magnitude of 2 degrees centigrade, which means a lot. So if you sum the heating given by climate change plus the urban heat island effect, the result is that cities are the most risky environments for the increase of temperature that they experience in the past 30 years. And also the increase of temperature is driven by using air conditioning, using the heating systems, etc. So the fact that it's local, because it's only within the city, doesn't mean that it's less dangerous, because people live in cities. So climate change may be local or global, and here you see in this figure an example of what happened to Tokyo. This is Tokyo is the yellow line, and you see during a period of 100 years the progress of temperature in several cities in Japan. And you see that the yellow one became the highest temperature, while at the beginning it was not the highest. The reason is that Tokyo increased much more in size, and this is the effect of the urban heat island. This urban heat island effect is a bit of a problem, because most of our measured thermometers, measuring instruments measuring temperature, are located within cities. So we have to, when we analyze the global warming, we have to try to separate the effect due to the greenhouse gases from the effect due to the urban heat island. Here I have given a box with an example of computation of statistics using statistical software. And what is the meaning of this yellow box? The meaning is to get you familiar with the computation of statistics through a software. I don't think you really need it, and I would propose to skip this for now. And then if I have time, I would like to go back to it, because I want to make sure that you have at least a very basic background that allows you to compute average variability and maybe some higher order statistics. It is a useful, I think, piece of information, no matter what is your degree program. Of course, if you are an engineer, this is trivial. If you are a mathematician, it's trivial as well, maybe even more, because mathematicians are the best in mathematics, of course. Maybe that if you are a student of social sciences, it's not so trivial. I think it is a nice, it's a nice way to make some attempts. And this is very simple. The only thing that takes like 5 minutes is downloading the software. And I just would like to spend a few words. You can make the same computation in Excel, no problem at all. Okay, so you get these numbers and you compute, you draw a graph and you compute the average. I think that if you try something a little bit more complicated, it's very useful. As I said, no matter what is your degree program, what I suggest you is to try this software, which is open source. You already understood that I like very much open information. I like very much open tools. So this is why I say, don't lose this opportunity to install and to try to use an open source software. You can also use LibreOffice, no problem, whatever is your. But in this case, an open source software which is dedicated to, in particular, statistical computing, which means climate analysis. Because, you would realize that it's much simpler than you could imagine if you are not If your study program is not a scientific one, you may think that things are more difficult than they are, for sure. And the same, likewise, we engineers, we think that studying literature, studying is impossible for us. Actually, I think that nothing is impossible. The only thing is to be guided and to get the proper introduction to it. This software, it's very easy to install. You click here, and then you go to download. And then you click on, okay, here there are some links. You take the first one that you want to get. Download for Windows. That's it. You can download for Mac, you can download for Linux. So let's forget about the other operating systems. I think you are familiar with Windows. You can download it. And then let me close this window. And here you have the instructions to make a plot and to compute average and variability. Variability is computed through the standard deviation. So this is an experiment that if I have time, I will get back and I'll do together with you. My suggestion for you, very, let's say, very quick homework, download the software and try to follow these instructions. As I said, if you are dealing with climate, it's extremely important that you can draw a plot of the data. It's extremely important that you can read a plot, okay? Okay, now, what is the cause of climate change? We have defined it. Now, let's see what may be the cause of climate change. First of all, we know that the climate of the Earth is changing. We know that we had glaciations. So what are the reasons for changes in climate? Let's focus first on the natural causes. Let's call them natural because it's, let's say, they are not human-induced. We will discuss later about human-induced climate change. So, the glaciation, we still don't know what caused them. We know that we experienced several glaciations in the past, and we will have a lecture on the history of climate. So you will see the magnitude of this glaciation. You will learn that we are still into a glaciation. We are coming out from the last glaciation. We are in the tail. And we don't know the causes. They might have been caused by variations in solar activity, changes in solar insulation. It could be the movement of the tectonic plates that change the climate. Because, for instance, we know that the separation between Africa, the European continent and African continent, European and African plate, and the American plate is widening the distance between these two continents, between these two plates, and therefore the oceanic circulation is changing. And this may be a cause of past climate change. Other causes are the volcanic eruptions. I think you remember the last big volcanic eruption which occurred in the north of Europe, which caused a change in temperature. Also, we couldn't fly for a while, and caused a change in temperature. And of course, climate change can be caused by human-induced alteration. There is no doubt that humans are influencing climate. I mean, it's clear. If you think about, if you think of the urban highland effect, is a clear demonstration. Again, there is no doubt on this. But a relevant research question is to recognize the extent of the human influence. Again, there is no doubt, nobody, no scientist negates the fact that humans are influencing climate. The relevant question is the extent, because we know that there is a natural variability, of course. And so the question is, what is the magnitude of human-induced changes with respect to natural variability? And this is called the climate change attribution question. It is extremely important to understand the interaction of human-induced change and natural variability. Natural variability is there, we know that. The interaction with the human-induced change, it is extremely important to decipher, because if they are in a way compensating each other is one thing. If they are summing up, it's another thing. And what I often say in the current debate about climate change, there is often the tendency to neglect natural variability. And what I often say is, if we do that, we get into big trouble, because we may underestimate what's going to happen in the future. And for some reason, and the reason is that the climate change problem is a controversial problem, for some reason there is, many scientists tend to neglect natural variability. Again, as an engineer, I say, look, if you ignore natural variability, you are really ignoring the problem, because it's very likely that they are summing up, I mean. So, I just would like to watch with you a couple of videos. They are very short. They are 5 minutes each. And I think it is productive if we have a look, because they give us, we dedicate 10 minutes, they give us a clear overview of human-induced causes and natural causes. Let me see if we can. Let me see if it's clear. You can read. Okay, I think we can stop here. And so what are the outcomes from this video? There is no doubt that humans are causing climate change, but let me say that, just 1 second, this survey is not very helpful for us. Just 1 second. There was a survey, I have to find it. Here it is. So this survey is not very helpful because what does it mean, principal? If we have to make a design, if we have to devise an action, we have to quantify it. So this survey to me is obvious. It's clear that I am almost, I would say that I am surprised that there is a 3% who says that humans are not the cause. It's clear that humans are the cause. But the question is how much? Also, there is another thing that I want to emphasize. There is no doubt that we are in a warming period. So let's be very clear with this. Nobody questions that. It's clear from the glaciers that are reducing their extension. It's clear from many signals. So no doubt that we are in a warming period. Still, there are some doubts about the magnitude of this warming, because, for instance, here, they are comparing proxy data or temperature data derived from other data from which we got an estimate of temperature. They are comparing this proxy data with the instrumental data, the red line. The instrumental data means temperature data collected with a thermometer, and we started only around 1850. We will talk again later about this. So comparing the two types of data, it's not really meaningful. In fact, you see the gray bar here. What is the gray bar? It's uncertainty. With the proxy data, you have a lot of uncertainty. Furthermore, if you estimate the warming with ground thermometer, you get an increase from 1990 of about 0.7 degrees at the global level. If you use the data from satellites, the increase is 0.35, half than that. So it's, the question is, what is the real increase? Because for an engineer, but let me say, for a person that has to find solutions, no matter the background, it's extremely important to be very clear. Another thing that I wanted to point out to you, when you see graphs like this, if you want to use a scientific approach, get used to observe the order of magnitude. So when we talk about the increase of temperature in the past 30 years, we talk of an increase in the range at the global level, 0.3, 0.7. It's not 10 degrees, because there are, I mean, sometimes I listen at conferences, somebody saying, it's clear, I perceive the warming. It's impossible. If you perceive the warming, it's not the warming due to climate change, it's something different. It can be the urban island effect, because 0.3, 0.6 is something that we cannot perceive. We can maybe perceive other changes, but not that. And it's true that in some locations, the increase has been twice. You have seen this map of the world during the video, which shows that the increase is not uniform. It's heterogeneous. So, for instance, in the Alps, it seems that the increase is about 1.5, twice the global increase. So 1.5 is something that you can really start perceiving. But again, get used to the order of magnitude of the variable and the uncertainty. Sea level. I just want to draw your attention on this graph, because I think it is very meaningful. Let me find it, just 1 second. maybe I missed it, just one. Okay, here it is. Sea level, how many centimeters are we talking about? From 1850, let's say that we start from an anomaly of minus 150 millimeters, and then we get to an anomaly, a positive anomaly of about 50. So we are talking about 20 centimeters in 150 years. It's not 2 meters. So this is something that really it's we have to take into account the order of magnitude. If you want to find solutions, I'm not saying that 20 centimeters is not significant. It's very significant. It depends on what you are looking for. If you look at drinkable water, 20 centimeters more of sea level means that you get salt water into the land, intruding into the land, which means that you cannot take your water for civil consumption from the wells. So in terms of groundwater, salinization of groundwater, 20 centimeters is a lot. In terms of coastal flooding, it's not much. Of course, it depends on the location, it depends on the extremes, but it's not really concerning from the point of view of coastal flooding, unless you have a very flat island. And it is extremely important if we want to find a solution to understand the order of magnitude. And I will discuss about this with you, because we are scientists and we have to understand what is the big problem, what is the problem, what is the minor problem. And of course, we need to give priority to the big problems. So it's important to recognize what are the big problems. So there is a question, please. And I repeat the question for the other students.
Maybe it's a little bit off topic, but what are the evidences that proves that those 3% of scientists reach deny the human impact?
Yeah, this is a long question, and I want to discuss about the controversial aspect of the global change, climate change question, and so maybe I can address this question later. But in any case, the evidence is the number of scientific papers, but actually the classification is a bit uncertain. There is a Wikipedia page, which I think it is linked here. Just one second. The question is, by the way, what is the evidence for the 3% of scientists who disagree on the human causes of global warming? And I think I have, if you want to get, just one second. Just one second. I think there is a link in the lecture. Somewhere on the global warming consensus. But in any case, I think you could find interesting information if you Google global warming consensus. You get how the statistic is computed. I just wanna, just one second, I share again the screen. Okay. And I just want to say a few things. It is based on the classification of the published scientific papers. But the problem is that nobody questions that humans are the cause of global warming. Many people question what is the incidence of human-induced global warming with respect to the natural variability. This is the big question. So if you just count the number of papers who say no to humans being a cause of global warming, of course you don't find papers. So I think that statistics does not give a real picture of what are the scientists debating, because some of them say, okay, humans are a cause of warming, but natural variability is much higher. And in any case, this paper would be classified in the 97%. So it doesn't give an idea. In fact, recently, some people claim that the consensus is 100%, precisely because nobody questions the fact that we are influencing climate. Yes, this is the controversial question. I just would like to show you the second video. I think it is extremely interesting to see also the second. Just 1 second. Okay. And let's see, you will see a lecture by Valentina Rossi on the history of climate, but let me give this overview. It's just 5 minutes. Sorry? Okay. Yeah. Thank you. Good suggestion. I was asked to put the subtitles. Ah, okay. Ok, un attimo solo che provo a vedere. Ok, condividi suono, perfetto. Grazie, non me ne ero accorto. Lo faccio ripartire perché sono confidente che... sorry, I start from here because I hope that you could, in any case, read the subtitles.
Ice Age, when several pulses of glaciation occurred over a span of about 100 million years in the Paleozoic era.
However, 3 million years ago, the distribution of continents was not much different from today, with one significant exception. Water was flowing freely between the Atlantic and Pacific Oceans through a narrow gap that separated North and South America.
That gap soon closed, and circulation patterns in the Atlantic Ocean changed, leading to more humid air carried further north and resulting in an increase in precipitation and the development of ice sheets in northern latitudes.
Contrary to what many people think, ice ages are not continuous times of extremely low temperatures. For example, examine this graph to see how temperature varied during the last 450,000 years. This includes the most recent part of the Pliocene-Quaternary Ice Age. As you can see, an ice age is actually characterized by a series of shorter climate cycles composed of alternating pulses of warmer and colder temperatures.
We can observe a series of longer cold intervals known as glacials that are interrupted by shorter warm intervals known as interglacials. These alternating cold and warm intervals reflect the advance and retreat of glaciers.
The interglacials last for 10 to 20,000 years. We may actually be in an interglacial now, or maybe the ice age has ended. We'll just have to wait about 10,000 years to find out.
If you look more closely at the graph, you can see that even within cold glacials, there are significant fluctuations of temperature resulting in colder and warmer intervals. All of these changes can be explained by small changes in the shape of the Earth's orbit and/or the inclination of the Earth's axis.
Temperatures in the polar regions become colder if Earth's orbit takes it farther from the Sun during winter, and if there's an increase in the tilt of Earth's axis. Over the course of tens of thousands of years, these types of changes have the potential to drastically change Earth's climate. When they all align in just the right way, they can lead to substantial warming or cooling trends to generate glacials and interglacial cycles, as well as shorter, more frequent cycles within these intervals.
Okay, so now we know that several long-lasting ice ages have been triggered in Earth's history due to changes in the relative positions of continents and oceans, and that climate cycles through warm and cold intervals during these events. But what causes an ice age to be sustained or to end?
We will consider the factors that help sustain an ice age to be positive feedbacks, and processes that lead to the end of an ice age as negative feedbacks.
Perhaps the most significant positive feedback arises from the ice itself. Ice and snow make very reflective surfaces. The term albedo is used to describe the reflectivity of a surface.
Bright, shiny, or light-colored surfaces have high albedo values and will reflect solar radiation. Reflection results in less solar energy being absorbed to their surface and produces a cooling effect.
In contrast, dark surfaces like forests or oceans have low albedos and will absorb solar radiation and become warmer.
Positive feedbacks in the climate system would result in larger ice sheets. Ice sheets reflect solar energy, causing less to be absorbed and leading to a decrease in temperatures, and thus sustaining the growth of the ice sheets and prolonging the ice age. Further, the growth of ice sheets would diminish the area of the globe covered by dark ocean waters and forests, further reducing the solar energy capable of being absorbed.
In contrast, negative feedbacks represent processes that result in an increase in temperature that would encourage melting of the ice sheets and the expansion of the oceans and forests. This might result from gradual changes in the distribution of continents and oceans, or from an increase in atmospheric carbon dioxide concentrations. Carbon dioxide and other greenhouse gases would trap heat close to Earth's surface, accelerating the collapse of ice sheets. Such an influx of gases could result from volcanic eruptions or from the decrease in photosynthetic activity due to cooler temperatures.
So for today, we had two learning objectives.
Okay, let me just again focus on a couple of things. First, even in this case,
Have to wait about 10,000 years to find out.
Get familiar with the orders of magnitude. So you see that what is the difference between the past max and means from -8 to +2. So we are talking about differences in temperature of about 10 degrees. In terms of sea level, we are talking about some 100 meters of elevation, just to understand what is the order of magnitude of the natural variability that we know. Don't miss the time scale. So when we talk about global warming in the past 30 years, we talk about 1 degree or less, but the order of magnitude is 1 degree in 30 years. Here, the time scale is millions of years. So, of course, it is also important to realize what is the time scale of the natural variability. This is the longer cycle. Then there are shorter cycles, but get used also to the time scale. One more thing, let me go here. There is one thing that I wanted, the feedbacks. The concept of the feedback is extremely important. And what is, I want to make sure that you understood what it is meant here as feedback. Feedback means that you make a change, and the change produces a side effect that increases the change itself. So you increase temperature in this case, you decrease the coverage of the ice sheet. By decreasing the coverage, you have a feedback that increases the temperature. This is extremely important. The feedbacks in the climate system, there are, again, positive and negative feedbacks. There are feedbacks that tend to compensate, and there are feedbacks that tend to increase the change. It is extremely important because what may happen here? It may happen that if we human induce an increase of temperature, then the natural system may react by exaggerating the effect, so further increasing the temperature. And then you have a further increase, which again, for the feedback, increases forever. And this is something that, of course, we have to avoid. Instead, the feedback of compensation, it is useful because if we make a change, then it may happen that the system compensates. And this is something that we have to well understand. Now, nature, by definition, is in equilibrium and tends to compensate. Why I'm saying this? Because if nature was not a resilient system, if it was a system that is not robust, it wouldn't be there. Because in the past, you know, we had some perturbations of the temperature, as you have seen, that were compensated by the system in some way. So nature is resilient, nature is robust, but still there might be a limit. There might be a so-called tipping point, which means that once that you exceed a given threshold, you cannot go back to the original situation. These complexities are to be understood, and let's be fully aware that we have still a very limited knowledge of the climate system and related feedbacks. So we are trying to understand, but climate science is a young science. It is a science that dates back to 50, 70 years. We are still in the process of understanding. Why I am emphasizing this? Because for us, it is extremely important, again, to get what is, in a way, certain and what it's not. So these feedbacks are extremely important. Okay. Let me now close this window. Just 1 second. Let me go here. Now, when did we get concerned about climate change? Roughly about 150 years ago, in the early 19th century, because we realized at that time, it was like 200 years ago, we realized at that time that the Earth experienced in the past ice ages. And then humans got concerned by this phenomena, of course. The greenhouse gas theory was outlined at the end of the 19th century. And the motivation was air pollution. After the Industrial Revolution, air got heavily polluted, and humans got concerned by the effect of air pollution, and therefore they postulated the basis of the greenhouse gas theory. And in the 1960s, the evidence for a warming effect due to the greenhouse effect became clearer. Still, around the 1970s, there was a decrease of global temperature. You can see in the graphs of global temperature that around 1970, for about 10 years, there was a decrease in the global temperature. And then scientists got concerned by a possible global cooling. Keep in mind that cooling from a point of view of natural disaster is much more dangerous than warming. And there is evidence for this, of course. And it's also clear if you look at the climatic condition and living condition in cold regions and warm regions, it's clear that in warm regions, you have conditions for agriculture, for industrial development, whatever, that are more favorable. And therefore, scientists were a bit concerned by this global cooling that probably was caused by an increase in the emissions of aerosols. And then global cooling ended up around the beginning of the 1990s, when the global warming started. And you know that it's now 30 years that the temperature is steadily increasing. Now, what is basically the conclusion of this reasoning and this voyage that we made through natural variability and the human-induced causes? The conclusion is that although we agree that humans are certainly a cause of climate change, we still have to understand what is the magnitude of the human-induced change with respect to the natural variability. And this is a very important research question, and you may see that the scientific community on this question has opposite views. I would say that the majority of the scientific community is convinced that the human-induced change prevails, but still the argument is debated. And if you go to numbers, it's difficult to say how much it prevails. This is something that we really need to understand, because in order to mitigate climate change, it's important to understand to what extent we should reduce the CO2 emissions by taking into account that CO2 emissions, reducing CO2 emissions, requires a substantial economic effort, which is to be paid by the citizens. So for climate change mitigation, we need this information, possibly in quantitative terms. For climate change adaptation, this is even more important. We need to know what is the magnitude of the change that we have to expect in the next 100 years. And if we make the mistake of neglecting natural variability, again, this is extremely dangerous, because it's not clear. I mean, we may be neglecting something that is more relevant, more important with respect to human-induced change. And the science today is researching on this. So there is no way of getting the reply now, but there is a way of devising alternative plans. And this is extremely important. Okay, and I want to give you an example before making another break. If you think about water resources, and I make this example because it's my field, what has been the main challenges recently? The main challenges around the world were given by droughts. And you may have heard of the Californian drought. In the media had a substantial visibility. There is a link in these pages on a Wikipedia page explaining the Californian drought. It lasted 4 years. It means 4 years with rainfall less than 30% of the average. You may have heard of the Australian drought. It lasted from 2001 to 2009. Both of these droughts reverted. They were declared closed. You may have heard, here there is a link, of the Dust Bowl in the United States and Canada during the 1930s. And if you open this link, it's an extremely interesting story, which brought many people to move, to leave their country, because it was a drought that caused a dust bowl. Now, these phenomena of long-term droughts lasting 5-6 years, we still don't understand. We don't know why they are happening, but they may happen everywhere. If you look at the rainfall in Bologna, we are lucky in Bologna to have a rainfall series that dates back to 1813, 200 years of daily rainfall. If you look at this rainfall series, you can see that for the whole period, sometimes every 50 years, there is a long-term drought. The last one was in 1950, from 1943 to 1950. And then we didn't have any so far. We don't know when this phenomena happened. Now, given that we don't know what is the cause, climate models do not reproduce it. So if we only trust on the assumption that we make on human-induced change, and we make design for the next 100 years, only basing on the assumption that the only concern is human-induced change, we neglect the risk of a long-term drought that may last for 10 years, which means that once that it happens, we are not prepared. It's like for the pandemic. We knew that a pandemic was likely to occur. Virologists told us since many years ago. I met by chance Ilaria Capua 2 years ago, and she told me, I'm really concerned because I feel that a pandemic is coming, but we were not prepared. So we don't have to make the same mistake for droughts, for long-term shortage of water. And therefore, this natural variability is to be understood. For some reason, today, we tend to neglect natural variability because we are more concerned by human-induced changes. But this is a mistake. Let me make a break again for 10 minutes, and then I'm teaching up to 6:30. Questions before we make the break? For understanding whether we are in the presence of climate change or not. Okay.
Sure. Thank you.
Yeah, no problem. Okay, so I think we can start again. First of all, I want to get a question from the chat. The question is, what is the difference between students that follow the lessons and who doesn't? I don't see any difference. I mean, the frequency is not compulsory. You are not obliged to attend to take the exam. So there is no difference at all. And I also would like to add that the information that you need to prepare the exam will be made available. Everything that you need will be made available. So you are not obliged to attend. Of course, I think that if you attended, it would be for you more rewarding because by attending, you have the opportunity to interact with the teacher, and the teacher usually provides additional information. We discuss. So there are additional information that I and the other teachers may give to you. This information is not necessary to pass the exam, but still it's part of your education. So if you are interested in maximizing your educational opportunities, I would say please attend, because this is the advice that I give to you. But if you are concerned by the exam, and I understand this is a reasonable concern, I would say don't worry, you can take the exam with a full mark, with the laude, without ever attending one lecture. So it's two different things. So to prepare the exam, you don't need to attend. If you have the opportunity, if I was you, I would attend because it's more information. And another question, two colleagues of yours mentioned to me that in the guide for students, there is still written that the final examination will be made through the presentation of slides. I'm sorry, this is outdated. I need to change it because this was the plan of last year when my prediction was to get 30, 40 students. With 200 students, I cannot organize presentation of slides because otherwise the exam would take for several days. This is not possible. So the exam will be in the form of a quiz, and again with a mark out of 30. Clear? Okay, so let's talk about the science of climate change. It's our interest. First of all, let me start by saying that climate change is a topical issue which ranks high in the agenda of politicians, policymakers, local administrators, whatever. And it's highly controversial. What is the reason why it's highly controversial while, for instance, water resources are not? Difficult to say. And there is certainly a political reason, political in the positive meaning. It's not a negative meaning. Political reason because climate change is seen as a global problem, while for some reasons, water is not seen as a global problem. still, I don't understand why, for instance, air pollution is not as controversial as climate change. You know, it's, again, the reason is probably the fact that there has been extremely high interest by the public and by the politics on the issue of CO2 emissions, probably because, you know, reducing CO2 emissions is a big political problem. Probably this is the reason why it's so controversial. It's a problem that has an impact on the economy. It's a problem that requires stepping back in our development. Reducing emissions today, if we want to take rapid actions, requires stepping back. Look at the pandemic. The pandemic caused a reduction in global CO2 emissions that it was something that we couldn't think of achieving in 30 years. Or let's say, not in 30, but let's say in 10 years, we couldn't think of achieving it. But we know the price that we had, and the price that we are paying, that we have to pay and that we are paying. The price is an economic recession. So probably this is the reason why climate change is so controversial. But still we have to be fully aware that it's controversial, and the fact that it's controversial doesn't help in being objective. So you have to be very aware of this. You are interested in a topic that is highly controversial. Whatever position you take, if you decide to commit yourself for promoting a reduction of CO2 emissions, you are criticized. If you decide to commit yourself for finding an alternative solution that doesn't require reduction of CO2 emissions, like there are some people who say, let's focus on adaptation. Let's forget about mitigating climate change. Let's put the economic resources in adaptation. These people are criticized. Conversely, people who say, let's put all the resources in mitigations, they are criticized because mitigation takes a long time. If we reduce CO2 emissions today, we bring them to zero, we expect to see the results in 30 years. And what happens during these 30 years? So I think we need a mix. We need mitigation. We need adaptation, because meanwhile, we need to solve the problem. We have people dying every year for floods, for instance. I am expert on floods, I know that. So we cannot wait for mitigation. We have to make a mix. But beware that this discussion is very controversial. How to reduce this controversy? And I would say interdisciplinarity. Open information, transparency. It must be clear, again, what we know, what we don't know. And this has to be clearly stated. If we know for sure that climate is changing in a certain way, let's make it transparent. If we are uncertain, let's make it transparent. Interdisciplinarity, because we need a full involvement of the communities of scientists. I think that a mistake that we are doing in climate change is that it is essentially a discipline that is dealt with by climate scientists. I think climate scientists alone cannot solve the problem. We need full interdisciplinarity, and in particular, you may think, of course, because I am biased, in particular, I think we need to involve engineering. Engineering has not been involved much in dealing with climate change so far. Usually, engineers are thought as those professionals that we give them instruction of what to do, and they have to make the design and put a signature certifying the responsibility. I oppose to this. I was called for some consultancy. I was said, look, please make a design in order to, by assuming that rainfall, extreme rainfall will increase 30%. And they said, sorry, I am responsible for this. I need to know how you got to plus 30% or minus 30%. So engineering should be more actively involved. This box explains what is engineering, but I assume you know. And Furthermore, let me say another mistake, which I think climate scientists, or let's say humans, are doing. In climate science, often we call into play consensus to provide support to assumptions and theories. Why do we call into play consensus? Because we are uncertain. We are uncertain on the basic research questions, which I will show you later what, in my opinion, are. And given that there is uncertainty, we call into play consensus, like the famous 97%. Now, the call for consensus is not new to science. It happened also in the past. There are very nice examples, like the evolution theory. The evolution theory is not rigorously proved. It is based on consensus, which is, something that it's fine. When it's not possible to prove something, we call consensus into play. But it has to be clear that consensus on a theory should not be confused with the rigorous demonstration of its validity. One thing is in math to prove a theorem. It is objective. Consensus is not objective and may be wrong, because we also have several examples. Think of Galileo, for instance. The consensus was proved to be wrong. There are several examples. So, consensus is fine, but it must be clear that if we call consensus into play, it's because there is uncertainty. And here there is a long discussion on this, which I'm not, please, this is another homework for you. I suggest you to read this page. It doesn't take much. It will take something like half an hour. And it is an integration of what I told you, and I think it will help you to better understand what I mean. So it is clear that climate science is currently under development. It is clear that there are several research questions that are open, and consensus is sought. We are looking for consensus, because, of course, as I said, when we are uncertain, a way to trying to minimize uncertainty is by consultation and search for consensus. But what are these research questions? And here I make a summary, which is subjective. This is my view. Again, it's not a research questions if humans are a cause of climate change. The answer is yes, they are. What are the research questions? Again, my view. I already said the first one. It's the interaction between human-induced climate change and the natural climate variability. How they interact. You may say, yeah, but we don't have the answer. Yes, correct. It means that we have to pay attention to the literature. It means that we have to develop an idea, and we have to be aware of the doubts. So, for instance, I think there is little doubt that global warming in the past 30 years, so that increase of 0.6, is probably mainly due to human effect. So if we study the literature, we see that for temperature, we don't have much uncertainty. But if we study the literature, we see that it's not clear at all how rainfall is changed. And therefore, it's not clear at all if the increase that we observed of floods is due to human-induced climate change. And we have to be fully aware of this, because one thing is temperature, one thing is rainfall, different things. Temperature, as I said, it's an easier process to model and to understand. Doesn't vary much in time and space. Rainfall is a mystery, is still a mystery. Rainfall is something that is extremely variable in time and space. You know what may happen in Bologna during summer. You have 5 minutes of rain, and then you get the sun. This is a process that is extremely difficult to understand and predict. Now, second research question, uncertainty assessment of climate simulation. And I put the emphasis for the sake of engineering design, because as an engineer, when I make a design, I have to put my signature, and I am responsible by law for this. And if I make a mistake, I have to present a defense in front of the court. And I have to explain how I estimated uncertainty. Unfortunately, for climate predictions, we still don't have a technical way of assessing uncertainty. The capability of climate simulations to reliably reproduce the frequency of extreme events, therefore avoiding underestimation, because it's not so easy. Some people say, okay, I know that climate predictions may be too skeptical, too pessimistic, but for the sake of safety, I rely on them. My reply is, okay, you are not safer if you rely on something that is uncertain and you don't know uncertainty. It's very risky, okay? Another research question, the capability for us to understand and then predict the risk related to the so-called black swans or tipping points. What is the black swan? It's an extremely rare event, which by definition is very difficult to predict. There are several examples. An example may be a volcanic eruption, or for climate, an example is an extreme tornado. Think about the Vaya tornado that occurred in October 218 in the Alps. How many trees were how many trees fallen? And the reason is that these extremes are, again, extremely difficult to predict. They are called black swans. What are the tipping points? We will discuss in a minute. And estimation of design variables. The design variables are the numbers that an engineer uses to make a design. And how to, again, I already mentioned this problem. How can I design a dam under climate change? There is no clue. This is an open question. And we are here for trying to get ideas. These are, I think, research questions that are extremely interesting, science question for devising actions. And now I would like to discuss a couple of things with more details. First, I gave a presentation to a conference 2 years ago, which was called The Unresolved Rebus of Natural Variability. The presentation is available for download. There is a link in this page. It is technical, and therefore, if you look at it, I suggest you to look at it, but you don't need to try to understand the details. Just try to understand the concepts. It's a presentation of, I think, 15 slides. It's very easy. It takes, if you don't focus on the details, it takes really 5 minutes. And I think it gives several examples of natural variability. I think it is extremely interesting. Of course, I am biased because it's my presentation, but anyway, you have to trust me, and then you are free to criticize. Now, what are the tipping points? Let me discuss a little bit, because I'm moving towards the conclusions and I'm not late for today. A tipping point for a given system like the climate system is a state of the system such that a small change of the state itself leads to a new equilibrium. And this is something that we know in ecology, in natural sciences, does exist. What does this mean? It means that, for instance, in certain regions, where we cut the forests. You know, if you cut a forest, you decrease evaporation. And if you decrease evaporation, you have less rainfall. And therefore, what may happen that if you cut the forest beyond a certain limit, beyond the tipping point, the rainfall, the remaining rainfall, is not sufficient for maintaining the remaining forest. And therefore, the forest disappears. And the region becomes covered by brushes. This is a typical change between two different equilibriums, the forested area and the brushed area. And the tipping point is that threshold that makes the difference. So if you get close to the threshold, then a small change brings you in the other equilibrium. Let me give you another example. And look in Google for Lake Aral disaster. This is not linked here. This is another interesting example. What happened there? The Lake Aral was, I think it was the fourth most extended lake in the earth. I'm not really sure. If you look in Wikipedia, there is everything. It was very extended. And the lake was, of course, originating evaporation and therefore precipitation that was feeding the lake. And then the former Soviet Union started to take water from the rivers, from the tributaries to the lake, because they needed the water for irrigating cotton plants. So they started taking the water, and the surface of the lake decreased because it was a quite flat lake. It was not very deep. So when a lake is very flat, if you withdraw even a small amount of water, the surface of the lake decreases. And then what happened? They reached the tipping point, because reducing the surface of the lake reduces rainfall and therefore reduces water into the rivers. They reached the tipping point, went over, and the lake almost disappeared. If you look in Wikipedia, you see that in 40 years, the lake almost disappeared because they reduced the surface of the lake too much, rainfall decreased, climate changed, and the lake disappeared, originating, of course, an economic disaster for the region. So this is another example of tipping point. A tipping point that may exist is related to the extension of the ice sheet at the North Pole. In the North Pole, we know that there is a lot of water into the ice. There are lakes into the core of the ice sheet. What does this mean? It means that if you reduce the extension and the thickness of the ice sheet, you may arrive to a tipping point where the inner water is released because we break the ice dam, which means that all of a sudden, a lot of water may be released by the ice sheet and may cause an increase or a rapid increase of the sea level. This is possible. In the South Pole, we don't have this risk. But in the North Pole, this is a possible tipping point. And the scientists are debating a lot on this. Because according to our understanding, we cannot predict this. We are trying to understand now with several researches, local inspections, if this occurred in the past. Because in the past, we had other periods in which the Earth was completely uncovered by any ice, even at the poles. So we are trying to understand how in the past the ice sheet melted down. And because understanding what occurred in the past may help us to try to predict. But currently, our climate models cannot reproduce this, cannot reproduce most of these tipping points. So this is an additional uncertainty that we have to take into account. So even if, we see that the sea level is increasing quite smoothly, it may happen that we have a sudden increase, and this is something that we don't have the capability to predict. Here in this figure, you see a lot of possible tipping, tipping drivers. Several possible reasons that may trigger the the activation of tipping points. And of course, to what extent, from a technical point of view, you have to take into account this. It is an open question. Should we consider any possible tipping point? But then the result is that probably we don't know what solution we can take. Because how can we really avoid this progress of the temperature, given that it's, even if we were able to stop the CO2 emissions, which is impossible, we cannot suddenly stop our CO2 emissions. Even if we were able to do that, it will take a long time before we can see the effects. So this is really an open question from a technical point of view, how to get to target. And what is a little bit depressing is that there is this controversy also ongoing, while I really don't see the reason why. I mean, in front of uncertainties, but of course, we can understand what could be. We can understand what is the reason. And also here you have an example of social tipping points, because tipping points may be defined in the natural environment, but also in the human society. Let me close by introducing a discussion on climate data. So we understood quite clearly so far that we need numbers to define climate change. We need data. We need a term of reference. Like one student asked me, but what is my term of reference? So when can I say that there is climate change? If I have an increase of temperature of 0.3 or 0.6 degrees at the global level, is this climate change or not? We need data, because climate change, remember the definition, is a change in selected statistics of climate. And therefore, a change can be detected if you have a term of comparison. We need data. The ideal situation would be that we had a lot of past data, observed data, not proxy data. Unfortunately, we don't have this plenty of observed data, because the observation of temperature in a systematic way only started around 1850, as I mentioned to you before. If we look at rainfall, the situation is even more concerning, because in Italy, we are very lucky. In Italy, we have long rainfall series, but with long, I mean daily observation of rainfalls. The oldest series is that of Padua. They started in 1713. So we have now 300 years of data. It is, for me, a mystery why in the past humans didn't have the idea of measuring rainfall. Measuring rainfall is extremely easy. You put a glass outside or a pot, and every day you go there and measure the height of water in the pot. In some days it's 0. In some other days there is water. You measure the height, you empty the pot, you put the pot there and take the measurement. It is extremely easy. But humans didn't have this idea up to 17th century, and it's 18th century. Sorry. So why is that? Probably because humans didn't have this need. They didn't have the need to measure rainfall, and the situation, our knowledge would be completely different if we had a rainfall series dating back 1,000 years. Actually, we don't. And therefore, we don't have long series of observed data. It's difficult to establish a terms of reference. So what is the solution to this situation? The solution is, first of all, let me show you this series. These are observed data. I mentioned to you before the series. It is a series of precipitation in Bologna. You can see here the annual values since 1813. And in gray, you see the long-term droughts. defined in a way that I'm not interested in the details now. So this is a very lucky situation. What you can see here, it seems, it looks like there is no obvious trend. It seems that rainfall overall is not decreasing. It seems that in the recent past, there is less, or let me say, there is less persistence. It's more variable, it's more up and down. In the past, it was more cyclical. Okay, one may say that we changed the observatory. It was in the center of Bologna up to, I don't remember the year, at the Specola Observatory, and then it was moved out of Bologna. But I don't think this is the reason why there is this change of behaviors. But still, it's very short. What may have happened in the past, we don't know. And so, how can we solve the problem of lack of data? We already mentioned the proxy data. And here you have an example of ice core data. If you take an ice core, you can, from the composition, from the concentration of isotopes, they are markers, in the various layers, you can get an estimate of temperature. So all the graphs that I have shown you before regarding temperature during glaciations, they have been created by using proxies. One possibility is the ice core, another possibility is 3 rings. Actually, these proxies are affected by relevant uncertainty. We already discussed that. And one thing to keep in mind, especially for 3 rings, they give a smoother indication, which means that you don't see all the variability, because sometimes 3 rings react to the weather after a lag time, and therefore you don't see all the variability. You get a smoothed representation, which means that variability is reduced. But of course, these data are extremely useful, and we have to take them into account. Finally, we have a third solution to the lack of data, which is using models. So when dealing with climate, you frequently hear about climate models reproducing what happened in the past, climate models used to predict the future. And actually, climate models, like any other mathematical model, can be a good replacement for the lack of data. But one thing we have to take into account for whatever application of modeling, every time that you use model-generated data, you have to be fully aware that they are only a surrogate of observations. They are affected by much more uncertainty with respect to observations. Observations are uncertain because we know that any measuring instrument is subjected to uncertainty. Models, much more. And we have to be fully aware that when we use model-generated data, the assumption, any model is conditioned by assumptions, any model is conditioned by the underlying equations, and we have to raise the problem of estimating uncertainty. For climate models, my personal opinion is that so far we don't have technically valid means for estimating uncertainty. Sometimes we are given ranges of prediction. This range of prediction still doesn't encompass in a satisfactory way uncertainty. This is something that is strongly debated. So you may listen from climate scientists that they are very confident on their observations, and this is often the terminology that they use. keep in mind that being very confident in a prediction is not a motivation that an engineer can use to justify in front of the judges a mistake. So we cannot say after a mistake, I was confident, because we have to prove in an objective way that we did all what was possible to estimate uncertainty. So feeling this responsibility, I say, and after having studied how uncertainty ranges for climate models are generated, I still say that it's not, I'm not satisfied by the estimates that climate models give. And one alternative way of saying this is the following reasoning. If you look at the simulation of the current climate by climate models, unfortunately, there is a big discrepancy. Of course, climate models are not meant to reproduce the observed climate. I know that, but still, I think that the comparison with the observed climate is a way to assess uncertainty. So when I see a big discrepancy in the reproduction of the observed climate, and this is particularly evident for the water cycle variables. For temperature, it is fine, but for rainfall, for snowfall, for water resources availability, unfortunately, we are still far from satisfactory performances. So just keep in mind that one thing is to make an assessment of climate change with respect to observed data. One other thing is to make an assessment based on proxy data. One third thing is to make an assessment based on model data. You will have another lecture given by me on climate models, and I think also Professor Navarra will talk about climate models, and this issue of uncertainty will be, I think, more deeply investigated. Finally, I want to discuss with you the, in 2 minutes, climate impacts. It's very, very short, and I want to emphasize that when we talk about temperature, the impact of climate change, once again, is quite clear. When we talk about other impacts of climate change, and now here I'm focusing in this figure on losses from weather disasters worldwide from 1980 to 2019. And weather disasters include floods, include heavy storms, include hurricanes, etc. You see a marked increase of the losses. So this is an indication that climate change may have had an influence. This also includes droughts. On the other hand, if you divide these losses by the global GDP, gross domestic product, you see that the situation becomes flatter, which means that a question then is raised. Is the increase of losses due to the increase of frequency of the disaster, or is it due to the increase of the value of the affected goods? This is something that is very relevant. This graph, I draw these two graphs by reproducing the data that I could take from an open access repository. But actually, the two graphs were depicted in a recent research contribution, published paper, which I think it is extremely interesting because it tries to analyze whether climate change has an effect, a direct effect on the impact of weather-related disasters. And from my point of view, this is essential because the solutions are different. I mean, if the increase is in frequency, the solution to this increase of the damage, of the losses, is different with respect to the alternative possibility that the increase is due to an increase in exposure, an increase in the value of the affected goods. The solution is different, it's clear. And this is something that, you know, it's a good example, I think, of the uncertainties that we still have on the impact of climate change. And just to conclude, I want to give you another example. In Italy, we are much concerned about the water bombs, the bombe d'acqua, as we called them. Now, we are struggling to find data evidence that proves that in the past 20 years, we had this surge of water bombs. The data don't tell us anything. And this is something that it's really amazing, because we can all perceive that there is something ongoing with this extreme rains. But the data that we have don't show any evidence. So there are two possibilities. Either the data are insufficient to detect the evidence, which may be the case, or the evidence is different from what we perceive. And this is a relevant research question. Are water bombs real? The scientific community is discussing. Now, any question? Okay, next time I want more questions. And next week I'll be the teacher again. I will focus on climate models plus probably something more. And while 1 week later, Professor Veronica Rossi will teach about the history of climate. Last call, any question?